Okay, so this is another problem out of Griffiths Quantum Mechanics Volume 3, or Edition 3, whatever. It's problem 7.17 out of the textbook, and we want to use a relativistic correction to the energy levels of a one-dimensional harmonic oscillator. Alright, so before I start, I will be doing more videos on solutions out of Griffiths Quantum Mechanics, so if this is something that either helps you with your homework or just something you find interesting to learn about, please like the video, and if you wouldn't mind subscribing, I would greatly appreciate that. Okay, so I'm going to go ahead and get in the problem, and I included problem 4.48 just because it has a theorem that we're going to use, and we actually used it in the last one, 7.17, but we used for the case of a hydrogen atom, in which case the expectation of your potential is 2 E sub n. But for a harmonic oscillator, it's a three-dimensional harmonic oscillator, but it applies all the same. It's E sub n over 2. So that kind of confused me when I was first trying this problem on my own until I realized the distinction, so I just wanted to make note of that. All right, so let's go ahead and get started. So the relativistic correction to our energy, the first correction, is minus 1 over 2m c squared e squared minus 2 e times the expectation of the potential plus the expectation of your potential squared. So this is equation 7.54 in the book. If you guys are interested in where these equations are coming from, I kind of did this just on my own to help me better understand, but I'm not opposed to in the future maybe going more into like why this is what it is, kind of like I did with some of the earlier mechanic problems, but for right now I'm just kind of grinding problems to prepare for an exam. So just if you're wondering, don't worry too much about it. If you are worrying too much about it, then maybe that's something I can work on in the future. So we know the potential for a harmonic oscillator is 1/2 m omega squared x squared. And you could then think of the expectation of your potential as being 1/2 m omega squared, and then the expectation value of x squared. Now real quick, I'm going to go ahead and use our theorem here, which says that our expectation value of potential is equal to your energy divided by 2. And if I plug that into here, then our first order relativistic energy correction is negative 1 over 2 mc squared e squared minus, well, the 2's will drop, and then you're going to get a minus e squared plus the expectation value of your potential, the expectation value of your squared potential. So obviously we see what happens here, but the reason why I just wanted to show that is because what I'm really interested in is the potential squared, since it ends up dropping out that way. So what we really want is just this. Okay, so that's kind of what I was just going to show. So now, with that in mind, coming down here, the expectation of our potential squared, just squaring everything, is 1/4 m squared omega to the 4th, the expectation value of x to the 4th. Okay, so all we did was we squared our potential there. And if we plug this into our new energy correction, the first order relativistic correction is minus 1 over 2 mc squared times 1/4 m squared omega to the 4th expectation value of x to the 4th. Okay, so how do we find the expectation value of x to the 4th? Well, by definition, this is just the inner product of our size right? This is the definition of an inner product. I guess it's one-dimensional, so dx. Okay. All right, so we're going to do the Brouquet notation, and we're going to use, because it's a harmonic oscillator, we're going to use the ladder operators. And this is what the ladder operator is equal to, in case you forgot. It is in the textbook if you need it. And x hat is just x, so I'm not really too worried about that. Okay, so I think this is basically the little hint they were giving you on use this technique, because with this ladder operator we can actually find our x value. So this is the raising or lowering depending on how we want to do it. If we do a raising operator plus a lowering operator, and you add these together, well, what will happen is your momentums will drop because the sign changes here. You'll have a minus and a plus, that'll go away. But the x is always positive. The x is always positive. So this is equal to 1 over 2 h bar m omega. That's what they have in common. And then 2 m omega x. And then you can solve for x. And if you solve for x, let's see, multiply that over divide. X is h bar over 2 m omega square root. The raising operator plus the lowering operator. So that's what x is equal to. And then x to the fourth, which is what we're interested in, well, you just have to raise everything to the fourth power. So that was square root, so now that's squared. And then this is to the fourth. Okay. So now we're going to go ahead and plug that into our what we have over here. Okay. So let's go ahead and plug that in. And when we plug that in, oops, that's our highlighter. We're going to get minus 1 over 8 mc squared, m squared omega to the fourth, h bar squared over 4 m squared omega squared, and then this to the fourth. Okay. So that was our energy over here. And we technically have this inner product. I'm not going to worry about this notation right now just because I'm a little lazy, to be honest. But just keep in mind that this is operating on a state. Okay, some wave function, but I'm just being a little lazy, so I'm not including it right now. But that will be important later. Okay. All right, so let's go ahead and simplify this a little bit, and then we're going to have to get into the messy part. Okay, our energy correction can then be simplified to minus h bar squared omega squared over 32 mc squared, and then this guy. Okay, so m squared, this will cancel with some of these, and then 8 times 4 is 32. Okay, so we're looking good. So now what we have to do is this evil thing. And again, this is operating, so these ladder operators are operating on some state. I'm going to bring that up in just a second, but let's go ahead and just see what this even is. So a plus plus a minus to the fourth, hopefully this doesn't kill me, is, maybe there's an easier way of doing this. Maybe I'm just doing a very like brute force way, but I'm just going to expand this. As awful as this is, it ends up cleaning up a little bit. But definitely not the funnest thing in the world. Okay, so now we're going to actually multiply out through this, which can be pretty messy. And you also have to be very careful because they are operators. So A plus. So I'm just going to go ahead and distribute like this. And then I'm going to do the same thing over here. Okay. So we'll get A plus acting on A plus A raising operating on the lowering operator, and then plus A lowering acting on the raising operator, and then plus A lowering acting on the lowering operator. And you're going to get the exact same thing here. All right, so that we expanded it, and now we're going to distribute this messy stuff. All right, so I'm just going to go term by term. So the two raising operators acting on the two raising operators. So that's A plus, A plus, A plus, A plus. And then these two now acting on this, plus, A plus, A plus, A plus, A minus, plus, I'm just going to move down to this one, A plus, A plus, A minus, A plus, and lastly, for that section, A plus, A plus, A minus, A minus. And then I'm going to move on to this one and do the exact same thing, so you can see how awful this is going to be. Do this in a different color, actually. Let's do it in red, I guess. So this will be plus A minus, and that'll be on A plus plus. This will clean up, though. Plus A minus, A plus A minus, plus A plus A minus, A minus, A plus, and I think there's one more, A plus A minus, A minus, A minus. Okay. Now we'll do the next one. Well, it looks a little too close to red. Maybe that was red. Let's try to do orange. Okay. So plus A minus A plus, A plus A plus, plus A minus A plus, A plus A minus, plus A minus A plus, A minus A plus, plus A minus A plus, A minus A minus. All right. And then in blue, we'll do the last one. Plus A minus A minus, A plus A plus, plus A minus A minus, A plus A minus. A lot of places to go wrong here. Plus A minus A minus, A minus A plus, plus a minus a minus a minus a minus. So you might look at this and just think like, man, I picked the wrong degree. But it cleans up quite a bit. And the reason why is I was a little lazy with the notation, but these are all operating on a state. So these are all, you have n, each one of these, right? Because that's what x to the fourth really was. X to the fourth was, well, x to the fourth was this, but keep in mind, we actually wanted the expectation value. So you could think of, let me do this. You could think of this kind of being like, yeah, let's keep it green, just so color organization here. Okay. That's essentially what we had. Really not that much more work. I don't know why I was being so lazy. So then all of this is really like this. And hopefully you're okay with breaking this up into individual inner products. All right, so why am I emphasizing that so much? Because, so if I just call this, we'll call this NM. This is the Kronecker delta NM. In other words, this will be, all these other terms will be 0 except for the ones where n equals n. When n equals m, then it's just 1. And the reason I bring that up is because we have these operators operating on our wave function. And the raising operator, you get an eigenvalue of n plus 1, and it raises our state. And the lowering operator gets you an eigenvalue square root of n, an eigenvalue of square root of n plus 1, my bad. And an eigenstate of n minus 1. So the point I'm trying to get at is we're going to have these operators, but at the end of the day, this has to just be n. Because if it's not n, you're going to have a n state, and then something that's not equal to n ket state, which means it's going to be 0. So the clean way to simplify this is to look term by term and see if you have the same amount of raising operators as lowering operators. Because in that case, they'll end up canceling the states out. You'll have some eigenvalues to consider, but the state will just come back to n. So for example, this first state, do this one, that's pretty. That's going to be 0 because you're just going to end up with n plus 4. You'll have n plus 3 here. You will also have n plus 3 here. And then this one will be fine because you'll just be left with the state n. So that one will actually survive. This one would be n plus 1. It doesn't survive. This one survives. This one survives. This one doesn't survive. Hopefully this makes sense. This doesn't survive. This does. This does. This does not. This does. This does not. This does not. This does not. So even though we had this big awful thing, only 1, 2, 3, 4, 5 states actually, or only like 4 of them actually contribute. I think I did that right. Just making sure I'm not messing up on any. 1, 2, 3, 4, 5. I guess 6. Okay, so 6 actually end up contributing. The rest are going to get you this state. The other ones will get you this state, the ones that I put a check mark, which is just 1. Now, we still kind of have to work through this because there's going to be these eigenvalues that will contribute. So we're going to have to work on that. Okay? So anyways, a relativistic first order correction is going to be minus h bar squared omega squared over 32 mc squared And I'm going to write it out again without the correct notation because I'm a little lazy. But then I'll break it down. So that term survived. This term survived. Well, let me just make sure I'm not getting these wrong. A plus plus, A minus minus, A plus A minus, A plus A minus, A plus A minus, A minus A plus. Okay. Minus A plus, A plus A minus. And then the last one. Okay. So I'm going to break these down into each of their own problems. So let's start with, I'll call this 1. So for 1, we have A plus, A plus, A minus, and then the minus operating on n. So it'll be A plus, A plus, A minus, the square root of n, n minus 1. And then we're going to have another lowering operator acting on this. So we're going to get A plus, square root of n still. And then this lowering operator will get you the square root of n minus 1 in this state n minus 2, which this is just n plus 1 square root. Okay? Sorry, minus 1. So then we're going to have A plus, and then when we operate on this, we're going to get, when the raising operator, you're going to get the square root of n minus 1. Okay? So you're going to get n minus 1. I'll try to stay with the same color. And then the state. So it's raising the state back up to n minus 1. We're just kind of following these sets of rules here. Okay. And then there's also a square root of n, which the raising operator will get rid of. And it'll be n minus 1. Okay? So this will just be n minus 1 times 1, I guess, but I'm sure you guys are fine with that. We'll call this one, let's do it in a different color, 2. So hopefully it makes sense what I'm doing with the raising operators. I'm going to start going a little bit faster. So A plus, A minus, A plus. And then the lowering operator will get you this state. And then the raising operator, that'll just get you n back. And then the lowering operator will get you n square root of n. And then finally, n squared. So just n squared. Okay? We'll call this 3. Almost done. A plus, A minus, A minus. That'll be the square root of n plus 1. That's what the raising operator does. And then we'll have the lowering operator acting on this. So that'll bring it down 1. And then so you'll get n plus 1. That's your new eigenstate. Right? Because you're just taking the square root of whatever the state is. And then a minus, that'll get you, so we have n plus 1, square root of n, and minus 1. And then when this acts on it, we're just going to get n times n plus 1. Cool. Call this 4. A minus, a plus, a plus. The lowering operator gets us this. And I'm kind of moving fast on these, so again, I hope it's not too confusing what's going on. Hopefully it makes sense. Just trying to grind through this one. Okay, that's what the raising operator does, and then the lowering operator, so you'll get n times n plus 1. Perfect. Alrighty, let's move on to number 5. Might do 5 like right here. A minus, a plus, a minus. And then you have a raising operator here, so it's going to be n plus 1 square root. You just have to be very careful with these eigenvalues. It's very easy to get them confused, so you kind of just have to work through them, like, at least I have to work through them like this. Okay, so then let's see, we're just going to get n plus 1. And hopefully you can actually see now you're just getting the states back. You're just getting the state n back every time we go through these operations here. So a minus n plus 1, square root of n plus 1. You can see there's never n plus 1 at the end of the day. We're just left with the state n. So we get n plus 1 times n plus 1. Okay. And last one, number 6. We have a minus, a plus, a raising operator, n plus 1 square root, n plus 1. Let's see, we're going to get n plus 1 times n plus 2 square root. And then when we lower down these two, you're just going to get n plus 1, n plus 2, state n. Okay, so hopefully that makes sense. It's really just kind of going through the eigen equation here. And now what we can do is we can actually substitute this back into our energy equation. So I'm going to do that. So our relativistic first order correction minus h bar squared omega squared over 32 mc squared is going to be n times n minus 1 plus n squared plus n times n plus 1 plus n times n plus 1 plus n plus 1 times n plus 1 plus n plus 1 times n plus 2. Okay, hopefully I did all of that correctly and I didn't miss anything. I think I'm okay. 1 is this, 2 is this, 3 is that. Okay. I think I did this correctly. Just double checking. I think we're good. 1, 2, 3, 4. 5, 6. Okay, yeah, we're good. I was getting kind of confused with what I wrote down, what I had here on the number list, but I think we're good. Well, let's go ahead and distribute. So that'll be n squared minus n plus n squared plus n squared plus n plus n squared plus n plus n squared plus 2n plus 1 plus n squared plus 3n plus 2. So let's just kind of combine like terms. 1, 2, 3, 4, 5, 6. So that's 6n squared. Let's see, these drop. 1, 2, 3, 4, 5, 6 plus 6n. And then just plus 3 for our constants, the plus 2 plus 1. Okay, so our relativistic correction is minus h bar squared omega squared over, let's do this. We can actually factor out a 6. So we can factor out a 3, sorry. 3 over 32, which does not go into that, so keep it like that. H bar squared omega squared over mc squared. And we factored out a 3, so it'll be 3n squared plus 3n plus 1. Suppose you could try to factor that if you wanted. I don't really want to right now. I think that's more than good enough. Okay? So, very tedious problem. A lot of work. But hopefully that makes sense. We started by simplifying our relativistic energy correction using the fact that the expectation of our potential was our energy over 2. And then we realized we just had to find the expectation of our potential squared. And the way that we found that was by using our ladder operator, since this is our harmonic oscillator. So we found x in terms of our raising and lowering operators and substitute that into our energy equation with some lazy notation. We expanded our ladder operator. We used the eigenvalue equations for our raising and lowering operators on our hydrogen atom. Or this isn't the hydrogen atom, but it works for our harmonic oscillator, sorry. And we used the fact that the inner product between n and m is the Kronecker delta. With that, we were able to simplify this absolute mess. We used, like I said, the eigenvalue equations. We substituted it in. We simplified as much as we can, and we were able to get this energy correction. So hopefully that makes sense. Like I said, I'll be posting a lot more quantum videos. Spring break for me, so I'll be posting quite a few. And if it helps you, please like and subscribe. Or if you're just interested in this video, these type of videos, I'd greatly appreciate it.